So now that we know that all the theorems that we've used about discrete time martingales extend to continuous time continuous martingales, we can see that the applications we had to random walks in discrete time will extend quite naturally to the Brownian motion in continuous time. So example of that, and that's the application we'll be discussing in this video. If I have a Brownian BT and I give myself two numbers A and B and I consider the stopping time defined in the following way, T of omega equal the infimum of those times for which BT is equal to minus B or BT is equal to A. Right, so I want to find information on that stopping time, and I want to know what is the probability that the Brownian will exit the interval minus B A from the right rather than the left, and I want to know what is the expected time at which it would happen. And we're going to show that just as we had for the random walk in discrete time, the probability of exiting through A rather than minus B is B divided by A plus B, and the expected time at which this happens is A times B. Right, so we're going to prove this in the context of Brownian motion. Now, if you remember, a key part of that was to use the stopped martingale theorem in discrete time. We're going to use, of course, its continuous time version. We're going to use the fact that the Brownian is a continuous martingale. But before we can do any of that, we need to make sure that the probability of tau being finite is 1, right? That was one of the key things that we needed in discrete time. So let's prove that first. So that's going to be 1, 2, and 3. And 1 will be the probability of tau being finite is 1, and actually the expectation of tau is finite. Tau is in N1. Okay, so how do we do this? Well, similarly to what we did in discrete time. So to prove 1, we consider the events of the following form. The events EJs, which are the set of all those omega for which, I should have said at omega here, for which bj plus 1 of omega minus bj of omega is greater than a plus b. So what does that mean that you're in this event? That means that between times j and times j plus 1, the Brownian has made a jump that is at least of the size a plus b. So wherever it might have been inside this interval, somewhere here, if it jumps by more than a plus b, well, either it's on that side or it's on this side. At any rate, it has left the interval because the length of the interval is a plus b. So, remark omega belonging to EJ implies that if the Brownian was in EJ, then it's not. Was in the interval minus BA, then it's not. If BJ belongs to minus BA, then BJ plus 1 doesn't. Right. Okay, and remember that the Brownian is almost surely continuous. So if you exit the interval, throwing away a set of measure 0, you would have to hit the point minus b or the point capital A. Right, so let's give a name to the probability of EJ. Let's call that epsilon. And notice that this is independent of J because the increments of the Brownian are IID Gaussian variables, right? So this is equal to P of EJ for all J, since Bj plus 1 minus Bj as a family index by n is a family of IID variables. Independence, guarantee that the probabilities have to be the same. Okay, and this probability is non-zero because the IID variables with B1, which is B1 minus B0, being an N01 variable, so the IID N01. Okay, now there is this epsilon, it's a positive number. What can I say about the probability of tau being large? Say the probability of tau being greater than n plus 1. So for some n, a natural number. Now, if the exit time tau is greater than n plus 1, it means that, well, you haven't exited the interval between time 0 and time 1. And remember that at 0 you're within the interval because b of 0 is 0. And then you haven't exited between time 1 and time 2, and you haven't exited between time 2 and time 3, and so on and so forth. So this probability is certainly smaller than the probability of the intersection of the complements of the EJs, right? If you were to be in any of this EJ, then you would exit at time, between time j and times j plus 1. So if you haven't exited by time n plus 1, that means you've never been inside one of these EJ. And by you, I mean you're the omega, and you're not in the set of measures 0 where the Brownian is discontinuous. Okay, so this probability of this intersection of complements, well, remember that the set EJs are independent because of the fact that the increments of the Brownian over disjoint intervals or intervals that touch only at one point are independent variables. So what we have here by independence is the product from j equals 0 to n of the probabilities of the complements of EJ. And what is that probability? Well, it's 1 minus the probability of EJ, which is epsilon, which is some positive number, obviously smaller than 1 because it's a probability. So this is 1 minus epsilon raised to the power n plus 1. Okay, and the point is that goes to 0 as n goes to infinity because epsilon is not 0. Okay, so what do we get? We get that the probability of tau being infinite, if tau is infinite, well, in particular, it's greater than n plus 1 for some n plus 1, for every n plus 1. So this probability has to be smaller than the limit of the probability of tau being, greater than n plus 1. Because if you're infinite, you're certainly greater than n plus 1 for all n plus 1, and that is 0. So the probability of tau being infinite is 0, therefore the probability of tau being finite is 1. That proves the beginning of part 1, that tau is finite almost surely. I also want to show for the applications I'm going to use later on, that it has a finite expectation, this stopping time tau. And again, that's the consequence of the fact that not only do this tail probability of the stopping time tau go to 0, but they do go to 0 extremely fast, right? They go to 0 like an exponential. And that's why the expectation of tau would have to be finite. Tau would have to be an L1 variable because it has such fast decaying tails. So let's check that out. The expectation of tau is the integral from 0 to infinity of the probability of tau being greater than x dx. Right, well, you can recompute that by explicitly writing this probability as an expectation, exchanging integrals. It's the usual trick. And what is this? Well, let's compare that to the probabilities that we've just computed. So we could decompose this integral from 0 to infinity as a sum from j to j plus 1 of the probability that tau is greater than x dx. And if tau is greater than x, well, and x is between j and j plus 1, then it's certainly greater than j. Right, so the probability of being greater than x is smaller than the probability of being greater than j. And what is that? Well, because of what we've proven before, this is certainly smaller than the sum from j equal to 0 to infinity of 1 minus epsilon raised to the power j. And that sum is finite because it's a geometric series. And 1 minus epsilon is a number strictly between 0 and 1. Okay, so that proves 1. So now we turn to part 2. And if you remember the way we've proven the analog of part 2 in the discrete time setting, we've used the fact that the analog of bt was a martingale, then the analog of tau was a stopping time, and then we say that bt minimum tau is a martingale, and we use the fact that it therefore must have constant expectation over time, and therefore the expectation has to be 0, and exploit that. So we're going to follow the same scheme here, but in order to do that, we need to know that tau is a stopping time and bt is a martingale, and then apply the stopped martingale theorem. So the problem here is that I haven't shown yet that tau is a stopping time, right? I kept talking about it as a stopping time so far, but I've just, proven properties of tau as a random variable. It's finite almost surely, and it's in L1, but I haven't actually shown that it is indeed a stopping time with respect to the Brownian filtration. So let's start with that. Let's take an x, non-negative, and consider the set where tau is greater than x. And I need to show that this is an fx. Now, how do I do this? Well, tau being greater than x means that you started at 0 because b0 is 0, and you haven't got out of the interval minus b to a in that interval of time, right? Well, at least if you look at values of omega for which the trajectory is continuous, because for a discontinuous trajectory, you might jump out of the interval without hitting the endpoint minus b or a. So first of all, let's get rid of this annoying discontinuous trajectories that have probability 0. So in order to do that, I'm going to define E to be the set of all omegas for which the trajectories are continuous, right? And then my set that I want to show is in fx is really the union of this set intersected with E union this set intersected with the complement of A. But remember that the complement of A has probability 0, and by definition of the augmented filtration, right, of the Brownian filtration, because this is included in EC and EC has probability 0, we have that on the set of trajectories that are potentially discontinuous, we are in fx. So that's not going to be problematic in showing that tau greater than x is a stopping time. That's one of the key reasons why we've augmented the filtration the way we did, to make sure that such exit times are indeed stopping times. So we only have to consider the set of all omegas in E for which tau is greater than x. Okay, but what is that, right? So if you haven't got out of the interval on a continuous trajectory before time x, it means, well, you've stayed in the interval up to time x. So what does that mean, staying in the interval? It really means that bt belongs to minus ba, and so what you need is to be in the intersection of all those set for t running between 0 and x, right? Up to the time x, you still haven't got out of the interval. Now, this intersection, well, it's the intersection of inverse images of an interval. So great. I mean, all of these inverse images are going to have to be in ft, and ft is included in fx because the family ft is a filtration. So you would think, I'm done here, but not completely. And I should have said, sorry, here it's not quite clear. This is the intersection of these things intersected E. And here that's that intersected A. That's not quite clear because the intersection is over an uncountable families of time. So I cannot just say the intersection of all these things in fx has to be in fx because the intersection is over an uncountable index set. But it's not really of an uncountable index set thanks to the continuity of the Brownian. Because if you're between minus b and a for a value of time t, then you have to be between minus b and a for a rational value of time close to t. So this intersection is really the same as the intersection over all times between 0 and x that also happens to be rational of the sets of omega in E, where bt of omega is between minus b and a. That's by continuity of t goes to bt of omega for all omega in E, right? So if you're in that open interval, you have to be within an epsilon of one of the endpoint, and then there exists a time, a rational time, such that you're also within epsilon over 2, say, within 2 epsilon of minus b and a. So this set of all the omega in E where tau is greater, when tau of omega is greater than x, is really a countable intersection of things that are in Ft. And the set of omega E in E such that bt of omega belongs to minus ba, that's an element in Ft by definition of Ft, and Ft is included in Fx. So what have we got? We've got that the set where tau is greater than x, which is the complement of the set, of course, where tau is smaller or equal to x, belongs to Ft. So this has to belong to Ft, and that means literally that tau is a stopping time with respect to the filtration Ft. Okay, so I do have a genuine stopping time. Notice that proving that it was a stopping time was not as straightforward as in the discrete time situation. The proof is very similar, but we had to deal with two potentially annoying facts. The fact that the continuous nature of the Brownian means you could potentially jump and not hit the endpoint of the interval. So we have to restrict our attention to the continuous trajectories and use the fact that we've augmented the filtration to get rid of anything that happens on the complements of E. And we also have to restrict our attention to E to then be able to restrict our attention to only rational times using the continuity of the Brownian. That's going to be the case in any proof we do really in this course about certain random variables being stopping time. So it's important to keep that in mind. The augmentation of the filtration is there to deal with that, and the continuity of the Brownian, the almost sure continuity, the fact that it's a continuous martingale, plays a critical role in such proofs, right? If you wanted to extend the theory beyond continuous martingales, and there are ways to do that, you will have to pay very close attention to the problems it causes to your stopping time theory. But that's not what this course is about. We're going to focus our attention purely on continuous martingales, which is already a very large class of stochastic processes. Okay, so now that I have that tau is a stopping time, I want to apply the stopped martingale theorem. Now, by the way, let's recall that Bt is indeed a continuous martingale. A continuous martingale. Well, continuity really is a part of the definition of what a Brownian motion is. And let me just recall that if you look at the expectation of Bt minus Bs given Fs, and say t is greater than s, what do you get? Well, you get just the standard expectation of Bt minus Bs. That's because Bt minus Bs is independent of all the increments that came before it. So it's actually independent of the sigma algebra Fs. And because Bt minus Bs is a n0 t minus s variable, this has to be 0. So that's why the Brownian is a martingale, of course. Now, because the Brownian is a martingale and tau is a stopping time, bt minus tau is also a martingale. And what does that give me? Well, that gives me, so that's by the stopped martingale theorem. And what does that give me? That gives me that the expectation of bt minus tau is equal to the expectation of b naught, which of course is 0, for all t. Right, now can I get to the limit? Yes, I can, because I have that bt minus tau tends to, oh, I should have said first, yeah. So since tau is finite almost surely, then t minimum tau tends to tau as t goes to infinity almost surely. Of course, because tau of omega up to a set of measure 0 is going to be some finite number, so the minimum of that finite number in t, if you take t large enough, is just the finite number tau of omega. Now, by continuity of the Brownian, of t goes to bt of omega, for all omega in E at least, we have that bt minimum tau also tends to, let's say, at a point omega, tends to be tau of omega for all omega in E, right? That's exactly what continuity is for the trajectory. So, all right, so we have almost sure convergence of bt minimum tau to b of tau. Do we have convergence of the expectation? Well, that requires some argument like dominated convergence or uniform integrability, which we do have here, because as in the discrete time setting we have a domination. Bt minimum tau, right, if I'm at a time that is before the exit time, it really means that I am smaller than the maximum in absolute value of A and B. Right, and this is just a fixed number, and a fixed number, a constant random variable, is always in L1 on a probability space. And that's true for all t greater or equal than 0. So by dominated convergence, I have convergence of the expectation of bt minus tau. That tends to the expectation of b of tau as t goes to infinity. But of course this was constantly equal to 0, so the expectation of b of tau has to be 0. And now we're done, exactly like in the discrete time situation, because what is the expectation of b of tau? Well, there's two possibilities. B of tau can either be a or it could be minus b. So this is the probability of b of tau being a times a plus minus b times the probability of b of tau being minus b, but b of tau being minus b is exactly b of tau not being a. So what have we got? We've got a times this probability. It's the hardest part, this little arithmetic here. What is it? Minus b times 1 minus the probability of b of tau being a, and then you reorganize this equation and you get that the probability of b of tau being a is exactly b divided by a plus b. Now, I'm going to leave part 3 as an exercise, but I'm going to give you the steps in that exercise, although you could follow the discrete time situation, but let me remind you what the steps are. So first, you prove that bt squared minus t is a martingale, right? Just like we did in the discrete time setting, squaring our random walk was not giving us a martingale, but subtracting the variance to that led to a martingale. And you can do the exact same thing here in continuous time. Again, you're going to use the fact that the increments bt minus s for t greater than s are independent of the entire fs in the filtration. Okay, now having done that, you have that t is a stopping time, so you get by the stopped martingale theorem that the stopped martingale is still a martingale. Obviously, you need that to be continuous too, which you would get from the continuity of the Brownian itself, and of course the map t goes to t. Then you stop the martingale, and then you conclude that the expectation of b tau square, maybe that's another step, and then you use the fact that the expectation of tau is finite to deduce that the expectation of b tau square has to be the same as the expected value of tau. And then you compute the expectation of beta square, and you get from there that the expectation of tau has to be a times b. Right, so these are the steps, and this is a very good exercise.